I've been having a really nice time here so far. Okay, so I want to talk about constructions of hyperbolic surfaces with large systoles, so a problem in hyperbolic geometry of surfaces. And let me start by defining the title. So the object I'm interested in is the following. It's a systole of a hyperbolic surface, and I'll just restrict to closed hyperbolic surfaces. So if X is a closed hyperbolic surface, then the systole of X is going to be the length of the shortest closed geodesic on that surface. Length of the shortest closed geodesic on X. All right. So the cartoon to have in mind is something like this. If your surface looks something like this, then the systole would be the length of this curve over here. All right, and furthermore, notational point, I'll use the word systole both for the length of the curve and a curve that realizes it. So I'm going to put length in parentheses here. Okay, so let me start with some facts about this, about the systole. First of all, let me see. First of all, if I look at, so systole, I'm talking about closed hyperbolic surface here. Of course, this is a function that is well defined also for a marked surface. So this is a function that also lives on Teichmüller space. And if I look at this as a function from Teichmüller space to the reals, say, then, well, for one thing, it's obviously mapping class group invariant because it only depends on the isometry type of the surface. But more than that, it's continuous, but more than that, it's also something called the topological Morse function. I'm not going to use this in the talk, so I'm just mentioning it, but after that, I'm going to basically forget about it. And this is a result due to Acrut. One consequence of this is that you could theoretically, if you understand the maxima of this function well, you could theoretically use it to understand the topology of the moduli space of curves, the quotient of this guy by the mapping class group. So that's one thing. Another thing is that if I look in moduli space at surfaces that are at least epsilon thick, then that defines a compact subset of moduli space. So how do I write this? If I look at X, so all hyperbolic surfaces with systole at least epsilon, then as a subset of moduli space, so just to be absolutely on the safe side, moduli space here is, this is the set or of closed hyperbolic surfaces of genus G, G up to isometry. And as a so the subset of surfaces that have systole at least epsilon, this is a compact subset, which is an old result due to Mumford. In particular, this means the systole is a continuous function, so that means it has a maximum on the moduli space of curves. And most of this talk is going to be about the question, what should that maximum be? So what is if I look among all hyperbolic surfaces, closed hyperbolic surfaces of genus G, which one has the largest systole. Okay, maybe I should also note it doesn't have a minimum on the modular space. With a little bit of hyperbolic geometry, it's easy to construct surfaces of arbitrarily small systole of any genus. But I'm going to be interested in the maximum. So the first thing I should tell you about is that there is a trivial upper bound on the systole, namely the systole of a closed hyperbolic surface is at most logarithmic in the genus, and at most roughly 2 log g. By this symbol here, I mean it's bounded from above by a function that is asymptotic to 2 log g. You can see this very easily, so let me prove this. What do? You take your hyperbolic surface, you take any point on the surface, and you start expanding a disk around that point. So if I do that, at some point, of course, initially this disk is going to be embedded, and at some point it ceases to be embedded. Looks something like this. So what happens in that case? Once the disk is no longer embedded, I can draw 2 radii, connect up like this. I found and these 2 radii together give me a closed curve of length at most twice the radius. Now I know that the shortest simple closed curve is the systole. So putting that together, I get that at any point in my surface, the disk, the radius, the systole over 2 should be embedded. Is embedded. Now what does that mean? That certainly means that the area of this disk should be less than the area of the surface. Okay. That means that the area of the disk, systole over 2, at that point should be less than the area of x. Okay. Now the area of a closed hyperbolic surface is a topological invariant. This is 4 pi times the genus minus 1 by the Gauss-Bonnet theorem. And this I can also compute because I'm assuming it's embedded, so I just get a hyperbolic disk here, and the area of a hyperbolic disk of radius r is roughly e to the power r. So this is roughly e to the power systole over 2. So e to the power systole over 2 should be less than something linear in G, which is the same as saying this. All right. So it should be at most logarithmic, this maximum. And in fact, it should also be at least logarithmic, which is in a sense is surprising if you look at how simple-minded this proof is. But the fact is, you can construct infinite sequences of hyperbolic surfaces with genus tending to infinity and systole growing at least logarithmically. The first example of such a construction is due to Peter Boozer and Peter Sarnak. And they showed that there exist sequences of hyperbolic surfaces surfaces such that, first of all, the genus of these surfaces they tend to infinity as I let k tend to infinity. And the systole xk is bounded from below by a function that's asymptotic to 4/3 log g of k. And this construction, what this construction uses is it's essentially a number theoretic construction. So what do? You start with a specific type of closed arithmetic hyperbolic surface. So for now it doesn't matter so much what that is, but it means, for one thing, that your matrices have entries. The matrices in your Fuchsian group have entries in some number field, which means that you can take congruence covers, and those actually realize this. So these sequences of surfaces are sequences of congruence covers of a fixed arithmetic hyperbolic surface. Should also mention that this was generalized to a larger class of arithmetic surfaces by Katz, Schaps, and Wischner. Generalized to a larger class of surfaces. All right, and this is basically the state of the art. So this simple proof, we have no better upper bound than the upper bound coming out of the simple proof. And there are no examples of hyperbolic surfaces with systoles that grow faster than this. And actually, so Schmutz-Schaller, someone who has a lot of results on these kind of questions, actually conjectures that these number theoretic constructions should be optimal. So let me say conjectures 4/3. So then this is, so there is some belief and that these guys should be optimal. All right. So one thing, though, about these number theoretic constructions is that they're not very geometric, so they don't give you a lot of control of what your surfaces look like. So what I want to talk about now is some geometric constructions. So I'm not going to change anything about this. I'm not going to get surfaces with systoles more than 4/3 log G. But I want to look at some geometric constructions of surfaces with large systoles. All right. So, with such a question, the first thing you might want to try is a random construction. So, why am I saying that? There are many of these examples of these extremal types of extremal questions where random objects actually do very well. A famous example is expander graphs. Expander graphs ask for regular, let's say regular graphs with large spectral gaps, and random regular graphs actually have nearly optimal spectral gaps. So maybe if you do a random construction of surfaces, you get surfaces with large systoles. So of course this depends on the model. So the model there are multiple models around, but the one that I would like to look at is a model due to Brooks and Mackover. Yes. So what does this model do? This is it's a combinatorial construction. So ideally what you would like to do is you take some number of hyperbolic triangles and you glue them together randomly. And of course, if you would do this with some fixed hyperbolic triangle, you get issues, you get cone points. So what this construction does instead is you start with ideal hyperbolic triangles, you glue those randomly into a surface with cusps, and then you compactify the surface, and that gives you a closed surface. So let me write that down. So what is the construction? I'll make it slightly more explicit in a second. So what do? You take an even number of ideal triangles, hyperbolic triangles. Let me call this 2n. Then you glue them randomly. Which gives you a hyperbolic surface with cusps. So picture to have in mind, for instance, example, case n equals 1, so two triangles. I actually have three combinatorial patterns to glue those into. So I'm going to draw this topologically. So I could either glue them like this, which gives me a torus with one puncture. I could glue them like this, with which gives me a sphere with 3 punctures. Or I could glue them like this, which also gives me a sphere with 3 punctures. So the difference between these last two is in the pattern of the triangulation. Here I glue 3 sides of each triangle to the 3 sides of the other one, and here I pair the 2 triangles only along one side, and then I match these sides up afterwards. But of course the resulting surface is the same. Okay, so the goal is you pick a combinatorial pattern randomly. And this is easy because given the number of triangles, there's only a finite number of patterns. So picking them randomly, you can just take the uniform measure on the set of patterns. All right, and then step number 3, you compactify. And what is this? You just add points to the cusps. Which gives you a closed, I claim this gives you a closed hyperbolic surface. Of course, if you look at my 3 pictures, that's very false. Because if I could compactify these surfaces by adding points to the cusps, I get spheres and tori, so no way that I'm getting a closed hyperbolic surface. So this happens if the genus is at least 2, which turns out to be generic. So these kind of models are typically good for studying large surfaces. So you take large amounts of triangles. It turns out that if you let the number of triangles grow, this condition is almost always satisfied. All right. Yes, also. Yeah. So let me write before I get to sort of what these surfaces look like. Let me specify a little bit how this model works. So there's some things that I stepped over. First thing is, so what I want really is that given the combinatorial pattern that of the gluing, that defines an isometry type of a hyperbolic cusp surface in the first step. And in general, of course, I have multiple ways to glue 2 ideal triangles along their sides. How do you see that? So of course, in a hyperbolic plane, every ideal triangle is isometric to every other ideal hyperbolic triangle. So that's not the issue. But, so let me take the standard one. And then, of course, so if I want to glue one next to it, I might glue this one next to it. I might also glue something like that next to it, some other real coordinate. And so what I said before, the dotted triangle on the right is of course isometric to this other triangle on the right, but it doesn't automatically tell me that these quadrilaterals are also isometric. And in fact, they're not, because what can you do? You can draw perpendiculars to the side where you've glued. So if I do that here, the perpendiculars would meet. Now if I would do that out of the dotted triangle, the perpendicular would end up somewhere here. So these 2 quadrilaterals can never be isometric, and I also have a way to measure how non-isometric they are, because I can just take the signed distance between these 2 points, and this is called the shear of the gluing. So if I want the combinatorial pattern to define the isometry type of surface, I need to tell you the shears. So let's go back here. What I'm going to say is I glue them randomly means I'm going to glue them randomly with shear equal to 0. So I'm just going to set the shear to 0. This has another advantage as well. Something I also glared over. A general gluing with general shears of hyperbolic triangles does not necessarily give you complete metric, because there's a condition. You need that along every puncture these shears add up to 0. Well, if I set them all to 0, then that is automatically satisfied. So now what I've written is actually true. So that's one thing. Then I need to tell you a tiny bit what this compactification is, and I'll just do that in words. So hyperbolic structures are in one-to-one correspondence with conformal structures, complex structures up to biolomorphism, and a cusp is nothing else than a neighborhood that looks like a punctured disk in these conformal structures. And a punctured disk, I have a natural way to compactify, just add the puncture back in. This gives me a closed surface with a conformal structure on it. And then, if the genus is at least 2, the uniformization theorem spits out a hyperbolic structure. Of course, the cusp surface has an advantage in the sense that I can control the geometry of the cusp surface in terms of the combinatorics. And this closed surface that I get here comes out of the uniformization theorem, so a priori I have no control whatsoever on what the geometry is. So that's also an issue here. But I claim that this is a good model for closed surfaces nonetheless, even though it maybe seems slightly artificial. And the reason is an old theorem by Belyi, which tells you, so I'm going to rephrase that in this language, which tells you that if I look at the set of closed surfaces I generate, so I look at all combinatorial patterns of triangulations, and I glue them all and I compactify them all, I get some countable set of closed hyperbolic surfaces. This forms a dense set among all closed hyperbolic surfaces. So let me write that as follows: all random surfaces. So again, that's a countable set. Form a dense set among closed hyperbolic surfaces. And that's nice. And this is really, this is very, very false for the non-compactified surfaces. Because if I know the number of triangles and the genus, I know the signature of the surface, meaning that for every signature, I only get a finite set of surfaces here. And we know that there's a whole deformation space called Teichmüller space of such surfaces, so this finite set is never going to be dense in there. So the closed ones are the interesting ones, and the punctured ones are the ones I can control the geometry of. That's the... Okay. So that's an issue, but that will come later. So the first thing to note is, so like we've already seen in the picture for 2 triangles, the topology is not fixed. The outcome, and if I would take 4 triangles instead, I could even get disconnected surfaces, because I'm just saying all ways to glue these triangles into surfaces. So that includes 2 tori consisting of 2 triangles each, if I'm using 4 triangles. But that's not an issue. So let me write down some results. So the connectedness actually comes out of older work on random graphs. So this is a theorem due to Bollebash and independently Wormold in the 80s. Is that, again, I'm going to write that as a theorem about surfaces, the probability. We decorate that with an n, so this is the probability on the space of random surfaces built out of 2 n triangles. The probability that the surface is connected, this tends to 1 as n tends to infinity. So that's okay. And then there's a theorem. So now that we know that they're connected, there's only one more thing I need to know the topology. I need to know the genus of these surfaces. And this has also been worked out. So the best version of the theorem is due to Gambert. And I'm stating something weaker than what Gambert proved, but let me just say, if I look at the expected genus, so the average, again among all gluings with 2 n triangles, this is asymptotic to the number of triangles over 4, so n over 2, as n tends to infinity. So this justifies what I said earlier. This genus being at least 2 is not an issue. And Gamert actually proves something much stronger. So he gets really a result on the asymptotic distribution of the genus even. So he can say much more than this. But for now, I'll just stick to this one. So in particular, the upshot of this is this gives you a model for large genus surfaces. Okay. So now the systoles. So that was what we were originally interested in. So are these these random constructions give you surfaces with large systoles? And it turns out that this fails, and it doesn't just fail, it fails rather miserably. Namely, what you can prove is that if you take the expected systole, and now not being precise here, because again, now I'm talking about the geometry, so now theoretically I would have to say whether this is the compact or the cusped surface I'm talking about, but it holds for both. So let me just state it like this. With the average systole, this actually converges to a constant. It turns out to be roughly 2.48, but it doesn't matter so much what this actual constant is. And the fact is, random surfaces have constant systoles. So I'm looking for systoles that grow logarithmically in genus, so I would hope something logarithmic in the end. So I'm very far away from that random surfaces. So on the other hand, you could read this as an indication that this is not an easy problem to solve. You're looking for surfaces that are really rare. Of course, rare is in this well-defined sense with respect to this model. No one tells you that if you take a different model, you do get something better. Okay, so how? Don't want to. Sorry?
Do you know what that number is exactly, the limit?
Yeah. You can. I have no idea. Oh, yeah, I have no idea whether it's equal to some other number. So I can write it out. So let me. So I can write it out in a certain infinite sum of Cauchy inverses of traces of SL2Z matrices. So that comes from the following. So actually, how do you prove such a theorem? What you do is, maybe I should define that first. So what it turns out that, so there's a natural set of random variables. So Z, X, N. So that omega n is my space of random surfaces. And then I define these random variables by, so given a positive number, I define these random variables by counting. So this guy is going to count the number of closed UD6 up to length x on my surfaces. So Z x comma n of a surface in omega in my probability space is going to be the number of closed GUD6 of length up to x. So if I'm asking for the systole, if I'm asking that the systole is at least blah, then I'm asking is at least x, then I'm asking that this guy is 0, right? If this guy is 0, it means the surface has no curves of length less than x, means that the systole is at least x. So that's the probabilities that I'm interested in. Just to convince you that to do that, you should study the behavior of these random variables. And now let me. Right, so what actually goes into that theorem there is the following. Is that, let me say, I fix some number. So in the end, I want to look at the probability that the systole is at least x. I fix some number, and what I do is I want to look at the limits of this random variable. And the claim is then Zxn converges in, it doesn't matter, I mean, if you've forgotten this definition, don't worry, but it converges in total variational distance. It means some measure on random variables. It converges to what? to a Poisson random variable with mean lambda x. So what is this? A Poisson random variable is a random variable with values in the natural numbers. They happen to be defined by their mean. I'm not going to write down exactly what it is. One way to read this is, this gives you a formula for the limits. So what it actually says, if you want to know what is the probability that I have 20 curves up to length x, then this theorem spits out the number for the asymptotic probability. Yeah, of course, this convergence is as I let the number of triangles tend to infinity. So to answer your question more properly, I get an infinite sum of Cauchy inverses of traces of SL2Z matrices and Poisson probabilities. And that you can fill, I don't know, enter into Mathematica and then you get 2.48. And how you prove this is turns out you can actually control the moments of these random variables. So moment is the expected value of a power. So you can control the expected values of powers of these guys. And it turns out that if the moments of a sequence of random variables converge to the moments of a Poisson variable, then your random variables actually converge. This is a fact. This is not true. This also depends on the fact that they happen to converge to those of a Poisson variable. And having said that, I should also say, I originally did this with the method of moments, but by now there are more modern methods in probability theory. And together with Christoph Taylor, we've applied those, and then you can actually get you can get the same theorem, but then allowing also the length up to which you measure to grow slightly. Of course, it would be great if we could see what happens up to all curves of roughly length log n, because we hope that we can control the systole that way. And that, so far at least, isn't exactly true. But we can control curves up to length log of n, or equivalently curves up to length log of the genus. So this is, I should note, this is still very, very far away of log of n. For instance, this is smaller than log of n to the power 1 over a million. So, okay, so conclusion, random surfaces for this question are not a good idea, at least. So we should do something else. And for that, so that was attempt number 1. So now attempt number 2, which is joint work with Alex Walker. So what we're going to do is we're going to take this construction. So you take ideal hyperbolic triangles, you glue them in some combinatorial pattern, and you compactify. But we're not going to do it randomly, but in a slightly more controlled way. And then we're going to get surfaces with large systole. That's the goal. And in this case, it actually works. So, construction. Or, well, yeah, it's sort of an algorithm, what we get. Construction. Yeah, let me say, well, sort of an algorithm, and what you get is of hyperbolic surfaces with systole roughly log of g. So recall, best known constructions achieve 4/3 log of g, and the theoretical upper bound is 2 log of g. We can do log of g, but we get some extra control over the surfaces we construct. And I should maybe also say this is based on an idea from graph theory. So in graph theory, you can ask a very similar question. in the context of regular graphs, so graphs that have the same degree at every vertex, you can ask for the shortest cycle in your graph and try to make that as large as possible. And with exactly the same argument, but then translated to graphs, you get an upper bound that is twice the log of the number of vertices, but then logarithmic, the base of the logarithm depends on the degree. And very similar constructions, like the one of Boozer and Sarnak that I talked about earlier, also gives you graphs with a shorter cycle of length, roughly 4/3 times log of the number of vertices. And this is also the state of the art for graphs. So the gap is exactly the same. But there's an earlier construction, which is due to Erdős and Sachs from the 50s, which gives you graphs with shorter cycle, roughly log the number of vertices. So that's sort of the idea that we try to imitate in the surface world here. So what do we do? Before I say that, I should tell you how to measure. Now I should tell you how to measure lengths of curves. So the fact is, the combinatorics tell me the isometry type of my cusp surface. So I should be able to measure the length of a closed geodesic on my surface in some sort of combinatorial way. And that's true. So let me first explain how to do that. So what do you do? So you're given some curve on a... So these surfaces, of course, all come with triangulations, and, well, technically they're ideal triangulations, but I'm just going to draw them for this, like this for now. So I'm given some curve, so some curve gamma that runs over some number of triangles that, of course, needs to close up. So what can I do? First thing, to make this picture easier, is I can draw the dual graph to the triangulation. So I just add a vertex to every triangle, and I connect triangles by an edge if they share a side. And because of something that I failed to mention, namely, of course, you can also glue triangles into non-oriented surfaces, but I want oriented surfaces. So because my surfaces are oriented, these dual graphs come with an orientation, which in particular implies that I can say whether I turn right or left at every vertex. So, long story short, given a curve gamma, I can, by tracing it, I get a word in L and R. So, gamma, let's say closed, I get a word in L and R. And of course, this is a little bit of a lie, because if I start at a different triangle, then I get a cyclic permutation of my word, and if I traverse the same curve backwards, I get the same word read backwards and L and R interchanged. So I actually get some class of words in L and R. And now the fact is, from hyperbolic geometry, that if I set L equal to 1, 1, 0, 1, and R equal to its transpose, then the length, well, not exactly the length of gamma, but hyperbolic geometry tells you that there's a unique geodesic in your homotopy class, and it minimizes the length among the homotopy class. So the length of that curve as a curve on a hyperbolic surface is given by 2 times cosh inverse trace of my word divided by 2. So let's quickly check that this is well defined, because of course this class of words by this turns into class of matrices. But what is the equivalence? The equivalence is either cyclic permutation, which is fine because that leaves the trace invariant, or this inversion, reading the word backwards and changing L and R. That corresponds to taking the transpose, just because they're each other's transpose. So, and that's also fine for trace. So this is in fact a well-defined formula. And in particular, it allows you, I mean, of course, it's not a particularly pretty formula, but it allows you to measure length in terms of combinatorial data. And that's what we were after. And it also implies that if I look at the words of course, if I look at the words in L and R up to a certain trace, and if trace at least 3, that's a finite set. So if I want my systole to be at least, to correspond to something of at least trace 20, I get some finite set of words that I need to avoid in my triangulation. And as soon as I avoid those, I know that the systole of that cusp surface, is at least 2 times the cosh inverse of 20 over 2. Okay. And okay, so that gives me the length on the cusp surface. And now there's this fact, which is a result due to Brooks. And it tells you that if the systole of the cusp surface is large, the length of the curve, the corresponding curve on the closed surface, is close to that on the cusp surface. So actually, if I want to control the cusp surfaces, I can estimate them using the cusp surface. So systole cusped surface large. Large. This implies length. Being a bit vague here, but it works. Lengths of curves on factorification are comparable to lengths of curves on the cusp surface. So that's good. That means that now if I want to construct closed surfaces with large systoles, I need to construct cusp surfaces with large systoles in this combinatorial way, and then I'm done, because I know that the compactification behaves in the right way due to this result of Brooks. All right. So that's good. So that's what we're going to do. And now, the final thing about this construction, I want to sketch how the algorithm works. So the actual, there's a lot of annoying details, but the idea is not so hard to explain. So that's what I'm going to do. So first of all, the input of the algorithm is what I want to start with. I want to start with cycles of triangles. Cycles of triangles. So what is a cycle of triangles? It just means something, a gluing of triangles so that the dual graph is a cycle. So that would be something like this. All right, that's a cycle of triangles. This thing has a length because I can read off the word corresponding to the cycle and fill in this formula. So this thing has a length. And of course, so this is going to be the algorithm for the surface of systole, at least 2 cosh inverse k over 2. So and what this algorithm is going to do is going to take these cycles and glue them together in some way. So in particular, these curves that I start with are going to appear on my surface. So if I want to achieve this, I certainly need that these cycles of triangles all have trace at least k. Otherwise, this would make no sense. And furthermore, what I want the total number of triangles in these cycles to be large enough. And what large enough means is going to be clear in a second. Such that the total number of triangles is large enough. Okay. And then, okay. I should start with a new board. So that's the input. So what does it do now? So again, the goal is to take these cycles, and then every triangle has one remaining side that is not paired with another triangle yet in these cycles. So the goal will be to match up these sides in such a way that I do not create any cycles of trace less than k, because then I'm done. Then I get a surface. Then I get a surface that satisfies this. And then if I know how many triangles I started with, I get some control over the genus, so then I can compare the genus with number of triangles. So what does it do? It looks at the following. It's based on the idea of that you can sort of make bowls with these traces. So if I say I want to look at the bowl of trace at most k around the triangle. What is that? If I start from a triangle, so this is supposedly the side that is not matched with any other side yet. And then I walk away from the triangle in every possible direction. If I do that, that gives me some set of words. Right, I can just trace what happens. Here I go right first, and then maybe I go left, and so forth. So it gives me some set of words. Gives me some set of traces. So I can make sense of what it means that I can reach another triangle starting from here with trace at most k. That just means that if I read off the word until that triangle, I get a word that has trace at most k. So that gives me some notion of bowls in this triangulation. And so what I don't want, so suppose the word, so what I need to avoid is, suppose the word from here to here has trace at less than k. What I don't want is to glue this side to that side, right? Because then I've lost, then I've created this cycle here which has trace less than k. So this is what I need to avoid. So now comes the algorithm. So first step is initially there's a good chance that I have two triangles that are still far enough apart so that there's no walk between them of trace at most k. So, and if that is the case, I just glue them up. There are triangles, let's say x, y, far enough apart in this trace notion of being far, then you glue. Okay. Of course, this is not a good algorithm because this gets stuck at some point. So what do we do when it gets stuck? That's the crucial question. And what the idea is the following. So if I have enough triangles, so what does getting stuck mean? It means that I still have two triangles somewhere in my triangulation that both have a side that's not matched up yet. But these two triangles are too close together to match up. Then you're stuck if this happens. So suppose this happens. What can I do? I can look at the trace table around. So suppose these are these two triangles. This is x, this is y. They're both not matched yet, but too close to each other. What can I do? I can look at these trace cables around x and y. Now, if my number of triangles is large enough, I can control. So the claim is I can control the number of triangles in a trace cable. So if my number of triangles is large enough, then I know that somewhere in the distance, outside of these trace cables, there's two triangles still. But apparently, they already have all three sides matched because otherwise I could do step 1. Otherwise I could do this with x and that one. So what do? I just simply remove this one, and then if this is w and this is v, so they were matched, and what do? I just break them apart and glue one to x and the other one to y. So this depends on this large enough that I said in the beginning. This depends on having enough triangles. And what is enough? And enough triangles essentially depends on the size of these balls. Now, what is the size of these? So if not, I'm just going to write in this short. What do we say? Cut and re-glue. That's what I do in the way that I just described. And for that, I need that the number of vertices is large enough. What do so I need to know the size of a trace cable, but the size of a trace cable depends on the number of words in LNR that give me trace K. Yes?
So I have a basic question. So trace is not additive under matrix multiplication, right? So,
no.
So when you glue together, why do you need these traces to be far apart? How do you know that how the trace changes when you glue along the loop?
No, what I want is, okay, so every cycle, every closed curve can be homotope to some cycle in the graph. So systole at least x implies that I need to avoid cycles in the graph that have length x in this notion of length. But on the other hand, if all my cycles in the graph satisfy that, I know that no closed curve can possibly have length less than x. So what I need to avoid is having any cycle in my graph that carries a word on it that gives me too small a trace. So that's what I'm trying to do here. So what I want is, of course, what I'm doing is if I have a side that is still not matched, what I do is I look at all and another side, and I want to check whether I'm allowed to glue them. That means that I need to check that in all possible ways I can walk from here to there. I do not have a word of trace at most k. So that's what I'm after here. So what I need to control is these balls of radius trace k here. And I know, and this algorithm is based on the idea that these balls have a certain size, and if I know that I have more triangles in that size, then I can do this cut and paste trick. Meaning that if I still have two unmatched triangles, but they're too close to each other, then I know because I have more vertices than the elements in the because I have more triangles than the number of triangles in these two trace balls, I know there needs to be a pair of triangles that I'm allowed to match to them somewhere. That's the idea. So I need to control the number of elements in these trace k balls, which essentially comes down to controlling the number of words in LNR of trace at most k. And so this is just, so now I need to count certain matrices in so these are SL2Z matrices. So I need to count certain matrices in SL2Z with trace at most k. So that turns into some number theory problem. So, and what we proved is that, let me just call that nk. So this is the number of words in LNR that have trace at most k, but at least 3, because maybe I should say that explicitly. So L to the power, k is horrible. L to the power m is this matrix. So this is trace 2, so I in particular have infinitely many matrices of trace 2. But I have finitely many between 3 and any upper bound. So this is the number of matrices of trace at least 3 and at most k. And what you can prove is that this is big O of k squared log k. Doesn't matter so much. So the input here is a bit of number theory. It doesn't matter, even the formula doesn't matter so much. What matters is if I put this all together, then I get surfaces with the property I want, namely systole at least log g. Because what do I get? I know that I need to take roughly this many triangles. I know then that I get systole 2 times cosh inverse of k over 2 from my algorithm. But if I know the number of triangles, I get an upper bound on the genus. So I can compare the genus with the systole, and that's it. So that's how that works. So I think I have roughly 5 minutes left or so. So let me very briefly sketch another construction. So this is, again, while I'm erasing the board, let me say, so again, this gives you a little bit of geometric control as well, because you start with these cycles, and these cycles are never destroyed in the graph, in the triangulation. So that means that I can fix a couple of lengths beforehand. I can say I want some multiplicity for a certain length, and you can construct them like that. Okay, so the last thing I wanted to do is look at Panty Compositions. So I don't have enough time to explain how it works. It's another sort of combinatorial construction. But I'm happy to talk about that afterwards if anyone wants to hear. So what is the question? The question is, okay, now I know that surfaces with logarithmic systoles exist. Can I construct these surfaces in such a way that the systoles form a Panty composition? So one thing I should definitely say is that constructing surfaces where the systoles form a Panty composition is very easy, because what can you do? You take your favorite Panty composition, you shrink the lengths of all the curves to some epsilon small enough, and then I claim the systole will be epsilon. And why is that so? That's because of the color lemma. Any other curve is going to cross some curve in the Panty composition, and the color lemma tells you that if this curve is small enough, that the curve that crosses it needs to be very long. So it's easy to get surfaces with systolic Panty compositions. The question is, can you also do that with logarithmic systoles? And the answer is yes. So there's earlier work due to Boozer. I should say that he proved that there are surfaces with systolic Panty compositions, so meaning the systoles form a Panty composition, the lengths of the shortest curves form a Panty compositions, and systole at least root of log of g. So again, this is an infinite sequence of surfaces. And using some combinatorial construction, now instead of triangulations, is based on gluing pairs of pans together in some fortunate way. You can actually show that you can go all the way up to log of g. So what can you show? There are surfaces. Surface of course is a closed hyperbolic surface of genus G. Infinite sequences of with systolic Panty compositions. And systole, so what I was able to get is 4 over 7 times log of g. Let me just put a squiggle here. Log of g. Yes. Yeah, I think that's just a good point to stop. So thanks for your attention.